Cool. All right. So yeah, thanks for coming. I've given this talk like a couple of times at like ETH Denver and ETHCC. Usually only have like 20 minutes, and then there's like a lot of stuff that people want to dive deeper on. So we have a full hour here. And I guess my plan is to kind of go through the stuff that I've normally covered before, but stop a few times and let people ask questions. So there's this like ask a question button on the bottom right, and Dan and Hutch are in the group, so they're gonna help like moderate or whatever. So yeah, definitely like put your questions in as we go along the way, and then try to take some regular breaks and answer them, and then kind of go on whatever tangents, or like if you guys have other questions that we want to talk about, then we can do that. So just gonna share my screen. Cool. So yeah, so I've changed the title of this a couple times, but the overall thing is like, how do you get a parachain block from like a block on its own parachain into the relay chain and to be finalized? And so like, if you've looked into Grandpa or Babe or stuff like this, part of being Polkadot is that you have to follow the finality of the relay chain. And so you basically have to get some state information from your parachain into the relay chain, and then that's how it gets considered final. So just some other resources to look into. There's this article that I wrote that covers exactly this. Like I actually wrote the article first and then made the presentation. So it really like walks through this, but we'll have plenty of time to stop and like go into questions as we go. So when we talk about Polkadot, like we're looking at parachains as like a bunch of different shards of the system. And so the idea of this slide is really just to introduce some terms that if you've been in Polkadot ecosystem for a while, you probably know pretty well. But if there's anybody new here, we have this relay chain, just like the central chain. And then we have parachains, which are all these shards of the Polkadot system. And we also have parathreads, but not really going to talk about those much today. There's like a few differences, but generally speaking, just use parachain as interchangeable for parathread. And then we have these validators and collators, which we're going to kind of dive into how they interact and like what their roles are here. So from a very like introductory level, the collators kind of live on their parachain and the validators live on the relay chain, but they also roam around to various parachains as they go. So when we look at all of these parachains, each one is a shard. And so they all have their own state, and they all have their own state transition function, which is a little bit different than other sharded systems. So if you look at like ETH2, for example, every shard in ETH2 has the same state transition function, which is the EWASM smart contracting environment. So you can like deploy contracts on top of EWASM, and they have all these shards that will interact via the beacon chain, but they all just have this EWASM that you're talking to. And so, you know, we typically refer to that as homogeneously sharded. Whereas Polkadot, we've used this terminology for a long time, that we have heterogeneous shards. And so what does that mean? It really means like every shard is different. Like each parachain has its own logic, its own state transition function. So you're not really interacting with a smart contracting environment. You're interacting with the blockchain itself. And what makes it different from like a bridge solution is that, and like what actually makes this sharded is that you're sharing state and validation logic with the relay chain. So if you think about like back to Ethereum 2, they're all sharing validation logic. They all can validate this EWASM state transition function. And so in Polkadot, we're kind of taking like both sides of this, and it really depends. Like if you want to say this is homogeneous or heterogeneous, it depends how you're looking at it. So if you're looking at it from the outside in, like as a user, or looking at another parachain from a parachain, these are all heterogeneous. So each shard will have its own runtime, and you can have like, you know, the balances module, democracy module. Maybe you have like a smart contracts module, or you wrote your own custom modules, and you can kind of compose these however you want. And so we have all these different shards that have these different runtimes exposed. But from the inside out, if you're looking at it from the relay chain at all of these shards, they're all actually heterogeneous, because it's just one of the like interface requirements between the relay chain and the parachains is that you have to be able to compile your runtime to WebAssembly. And if there are any like parachain devs on here, I'm sure you're familiar with like, not using the standard library and all the constraints that go around being able to compile your runtime to WebAssembly. But all of this gets compiled in WebAssembly to the single execute block function, basically. And so if you're on the relay chain and you're looking at all these shards, you actually just see like a bunch of execute block functions. And behind the execute block is totally abstract logic. It's just like a blob block validation function, but they all look the same. And so when you talk about like homogeneous versus heterogeneous, it just depends like how you're looking at these shards. So if we want to get a block or like a state transition from one of these shards into the relay chain, we're going to start with the collators who are on that parachain. And so only one of them can submit a block to the relay chain at one time. And so it's really up to the parachain's logic of how they're going to select these collators. Actually, before I move on to this, just like from the introduction, like, are there any questions? Let's try to stop frequently. Okay, I don't see any. Oh, I'll send you the presentation now if you want it. I can't. Okay, never mind. I will, after the presentation, put it in a place where I can share it publicly. All right. Oh, there's no questions. I'm going to go back to here. So yeah, you have to select one collator to send your block to the relay chain, and how you do that is up to you. So you could use like proof of stake, proof of authority, proof of work. And it's important, like a lot of people talk about proof of stake as like consensus. So let's say like proof of stake consensus or proof of work consensus. But proof of work isn't really consensus. It's like proof of work is how you select who's going to make the next block. And then consensus is really like which chain are you building on. So, to continue the proof of work example, whoever can find some hash that's below a target difficulty, they're the ones who get to make that block. And so you could do the same thing in parachains. You could have some like difficulty threshold and make a proof of work parachain. But instead of that validator or that collator deciding like which chain it's going to add to, it's actually just like it gets to propose the block to the relay chain. And then it's up to the relay chain to decide like which chain ends up being final. So of course, like in order to send a block to the relay chain, they have to be like, they have to have a connection between the collators and the validators. So we haven't actually implemented this part yet where the collators and the validators find each other. But the validators get randomly assigned to parachains for every block. So you could have like 1,000 validators and 100 parachains, and you're just going to randomly assign like 10 validators to each parachain. That's going to actually change every single block. So on block 100, parachain 1 will have some set of 10, and on block 101, they're going to have 10 different validators. And so this just gets kind of like a couple. We use the Babe randomness beacon to actually make these assignments, but they have to find each other. So at the beginning of like a block slot, you have to kind of open these connections between the validators and the collators. And so we haven't actually implemented this yet, but there's kind of two ways to go about it. One is that the validators go look for the collators because they get their parachain assignment, so they kind of know how to find the collators associated with some parachain. You could have like entry nodes into this network, and then the other way around, of course, is that the parachains find out who is assigned to them, and then they have the DHT of the relay chain, and they can go find the validators that they're supposed to find. But one way or another, they find each other, open a connection, and then this collator who was selected will send a proof of validity to the validators who are in that group. So we're going to like break down what this proof of validity is, but just like a quick overview in case anyone's not familiar. Like we have a state tree, just like a tree data structure. So you have all these entries, which you can see at the bottom. So you might have like the free balance of Louise, like the validator counts, all these storage entries that are in there. And then, you take a hash of this, and then you get the leaf of the tree, and then you take the two hashes that are next to each other, you concatenate those, and you take the hash of those, and then you just keep doing that until you get all the way up to a state root that kind of represents the whole tree. So in this proof of validity, it's really just going to be like two things. It's going to be the parachain block and then some pruned state tree. So in the block, we have this list. We have like a header, and then we have a list of state transitions. So like, in this example, I chose, democracy uninitialized, which in this particular example, like there was a new referendum that was up. And so we increased the referenda count from 3 to 4. And then like a balance transfer from Louise to Ben of 50 tokens. So most of these items here didn't change. So we don't actually need to like send that information. We can just send that leaf, the hash of the tree. And then we only really need like the actual storage items of the ones that changed. And you can see we can kind of prune this tree down to just the storage entries that changed and then a bunch of hashes. So this is actually like all the information that you need to validate that this is a valid state transition. And you kind of know that the other stuff hasn't changed because the hashes. So just to kind of like back up, because this is on one block. So we've had, one parachain, sorry, not one block, one parachain. So like one parachain with 10 validators on it. One of the collators sent this big chunk of data, the new state tree in the block. But this happened, we have 100 parachains. This kind of happened in parallel 100 different times, and this hasn't been sent around the whole network yet. This is just amongst like the 10 validators who are within that group of the parachain. So we have this going on kind of everywhere at the same time. And then in order to move on to the next stage, where we propagate this to the rest of the Polkadot network, we just need more than 50% of that group of 10 to agree. And I'm using group of 10 as just an example. It would be number of validators divided by number of parachains. So I'll pause here again for questions. Anything? Okay, there is one. Can a third-party blockchain become a parachain of the Polkadot ecosystem later on anytime? Yes. So you really just need to implement this. You need two things really. Like one is that you basically need to agree to follow Polkadot's consensus for your finality, and then you need to implement your runtime so that it will execute in the Polkadot runtime environment, which really just means that you can provide this execute block, and then like Substrate and Cumulus will provide that for you. So like if you can build it with Cumulus, then it's automatically compiling to this function that you need. But you can definitely do it without Substrate also, as long as you can compile it into the proper WebAssembly. So yeah, the way you would like move another blockchain into Polkadot is you would basically have like a fork that says, starting in block, for now we're following our own finality, which could be proof of work or like our own proof of stake or whatever. And then, at block 10,000, when we're going to join Polkadot, we're just going to switch and say like, actually, we're following Polkadot's finality now. So that would be like the process of like transitioning into Polkadot as a chain that already exists. All right, so if you didn't notice, like this big thing of information is quite large. And different chains could have different amounts. So you could have one chain that has, like literally this example with like 8 items in their state tree, and then you could have another one that has a huge state tree. And we don't want certain parachains to hog this system. So, like if you look at a system like Ethereum or something, like one contract like CryptoKitties can kind of take over the whole system and like increase the fees for everybody, which is kind of one of the motivations for having your application independent chains. And so we don't want that to happen. We don't want like one super busy parachain to impact the other parachains. And so we really want something that's constant size. Like no matter how big your state transition is in your parachain, whatever goes on the relay chain is going to be the same size, or whatever, not just going into the relay chain, because actually like even less than this is going to go into the relay chain. But like whatever we're like passing around, we want that to be constant size, because this is going to be gossiped a lot between the validators. And so it puts quite a load on the networking if we're just sending like these huge POV blocks around. So that's why we put together this candidate receipt. And so like everything in here is constant size, basically. So like parachain ID, collator ID, these are like U32s. We have a bunch of hashes here. So like Merkle roots are hashes. Hash of the relay chain parent block. So you're kind of telling the validators like which relay chain, the relay chain potentially has forks that haven't been finalized yet. And so you're telling them like how you want to build on the relay chain. The Merkle root of the POVs erasure coding, which we're going to get to next. Merkle root of any outgoing messages, and then hash of the POV block, upward messages. So this would be like the one thing that's not exactly constant size, which would be messages from a parachain to the relay chain itself. So we're not talking about like parachain to parachain messages here. Those would just go in like outgoing messages, but we're talking about like if you want to send a message to the relay chain itself. And then any fees, which could be like if you're this is where like a parathread and parachain would be different. Parachain just kind of like gets to put one of these, gets to put a block into the relay chain, whereas a parathread has to like bid on it and like, win this auction to get the parachain slot for this one slot. And so they might have to pay some fees with that. And same with like upward messages. That's something we can't totally control the size of. I mean, we can say like, here's a max size, but then it can still vary block to block, but we could also charge a fee for it. So that's the only thing that's like not a constant size, but we can charge a fee for it. It's actually, so we're going to talk about the erasure coding stuff, but I guess like if there's any other questions like on this list of like what something is, now would be a good time to ask it. So any questions except erasure coding? Just give it a second. Okay, I don't see any. All right, so now we're going to take this erasure coding and we're going to take this POV block and we're going to make an erasure coding from it. So what an erasure coding is that we take like some message, which in this case is the POV block, and we make it a bigger message, but such that you can reconstruct it with like some fraction of the total bigger message. And so actually Jeff Burgess at Web3 had a really good way of explaining this, that like natural language is erasure coded. So like in your native language, this might be like very, it might be like so intuitive that you don't realize it. But if you ever learned a second language, this actually makes a ton of sense. Like I learned French a while ago, and at first when you're learning, like if a car drives by and you miss like one word from a sentence, you're just completely lost. Whereas after a while, yeah, there could be like some music playing, or you miss a couple words of a sentence, you can actually kind of like reconstruct what you missed based on the syntax that's around it. And so it's the same thing with this. Like you can reconstruct the message from, even though you're missing some pieces of it. And so the way that we set, like the nice thing in computer science is you can kind of choose this fraction, whereas in natural language, it kind of depends on the sentence and the speakers. But we can choose like, yeah, we want to make this message a little bit bigger and you need a big fraction, or we're willing to make this message much bigger, but only in a small fraction. So the way we do it in Polkadot is that we make it big enough so that you need 1/3 of the pieces to be able to reconstruct the total POV block. So we're basically going to take this POV block, make it a little bit bigger, send it out to all the validators. I guess we haven't sent it out yet, but like we're going to make one piece for each validator, such that if you had 1/3 of them, then you could reconstruct it. So if you have 1,000 pieces, then you need 334 of them to reconstruct the entire POV block. And it can be any 334. It doesn't need to be like a specific set. And so the thing that we're actually going to put into the candidate receipt here, when I said it's like the Merkle root of the erasure coding, we're just going to take these like 1,000 pieces and make another Merkle tree out of them and put the root of that into the candidate receipt. So again, like doesn't really matter how many validators there are in this set. We're still only putting like the actual Merkle root of this erasure coding into the candidate receipt. And so now what we have is we have like this candidate receipt that's pretty much complete. And then we have one erasure coding chunk for each validator. So if we have 1,000 validators in the network, then we have 1,000 different chunks, and we have one erasure coding. And we're going to just start sending this out to everybody. So everybody's going to get the same candidate receipt, and then like the actual erasure coding chunks are more targeted. So like, the validator who's validator 7 is going to get erasure chunk 7. And we're going to start sending these out into the network. It's only like one slide, but it's a lot of information. So I'll give another chance for questions here. No? All right. It took me a long time to understand that. So I hope I was able to make it like pretty clear. So now when we come to like, if you think about like the point of view of a validator now, this has gone beyond just like the parachain that you're on, right? This has been sent kind of across the whole network. So if you're a validator, you have all these candidate receipts and a bunch of erasure coding chunks, and then you have like your transaction queue with like the normal like dot balance transfers or like dot staking, stuff like this. And one of these validators from the relay chain is going to get selected to make a block for the relay chain. And so how are they going to actually construct this block? So we have this inherent, and if you're not familiar, like in the blocks in substrate clients, Polkadot is one of them. We have extrinsics is this like very broad term that includes inherents, which are things that like only the block author really puts in, and they're not really signed, like they're not gossiped around. And then we have transactions, which is kind of like your normal idea of a transaction of like somebody signs something like I want the stake or I want to send a balance transfer or something. So the actual update in the relay chain is an inherent that comes from the block author, and they're going to take all the candidate receipts that they have, and they're going to start to like update the block headers. And so in order to select like which ones they're actually going to update with, they're going to say like, okay, well, we have to have like a parent candidate receipt. Like we can't just take a block that doesn't already have a finalized, or it doesn't even have to be finalized, but you have to be building on a chain that has a parent to that block. And then the author also must have a corresponding chunk for the receipt. So I'll get into like a little bit later why availability, like why we're doing this erasure coding and why it's so important. But if you don't have a corresponding chunk, if you have a candidate receipt but you don't have the chunk for it, you're just not going to include that in your update. And so actually before we get to that, yeah, so like how does this update take place? So in this inherent, we have, it's called set heads, and basically like what is stored in the relay chain is the block headers. So it's actually like the block header is totally abstract. It could be the entire block header up to like some limit, or it could just be like a hash of the block header. But we need something to represent this block header. And it's just like a mapping from parachain ID to the current header. And so it's just going to go through, it's going to do a bunch of checks before it actually updates it. But for each candidate receipt that it has, it's going to like pass all these checks that we'll go through in a minute. But it'll just take its storage item and say, okay, for this parachain, I have a new block header for it, and it's going to update that. And so that's the state update that it's going to propose to the rest of the validators in Polkadot. And then now we'll talk about like how we actually accept that state update. So a few things we have to guarantee. We have to make sure that the validators actually receive their chunks and not just the block author. We have to make sure that they actually save them. And then we have to make sure that the blocks are valid. Because the person, so before these candidate receipts were sent out, the group of 10 validators that were like on the parachain, they've all attested to say that this block is valid. But the person who built the actual relay chain block, they haven't actually validated like all of these candidate receipts that's inside of them. So we need to guarantee that before we actually finalize it. So this is where the collators come back. Actually, stop for, I'll do another question check here. Yeah, there is one. Okay, I explained what erasure coding was, but not so much why we need it yet. Yeah, just another like quick overview. Yeah, so Alex, like in case you missed, yeah, the erasure coding is like we take the POV block, which is like the block plus the state update, and we're just going to create a new message from that, such that a smaller fraction, like such that 1/3 of those messages could reconstruct the entire POV block. So that's what the erasure coding is. So yeah, so actually, like now is when I'm going to talk about why we need this. So the like yeah, sorry. Yeah, the collators are going to start asking the for the chunks that correspond to their chain. And so I guess like before this happens, if you like, so say you're a validator and you receive a block and it has some candidate receipt in it, but you don't have an erasure coding chunk for it. We're going to have like some block limit that's called an availability grace period, where you basically like, if you're a validator and when you go through a list of candidate receipts, you should always have an erasure coding chunk for each one of those. And if you don't, then you're going to raise some flag and tell everybody, hey, I got this block. I had a candidate receipt for Parachain 7, but I never got a chunk of this erasure coding for this. And if enough validators say that they never got their erasure coding chunk, then we're just going to throw away that block like it's not good. So once we're through that, like once everybody is kind of happy that they have their chunks, the collators are going to start asking for them. And so they're going to ask for the chunks that correspond to their chain. And if they can't get enough of those chunks and reconstruct the block, then they're going to report that it's unavailable. And so this is like the fun part. This is why the erasure coding is important. So if you imagine like a malicious collator, they're sitting around and they're waiting to make their block. And then what they do is they just make their block, they give it to the validators, and then they go offline and then just like, unplug, drop off, gone. What you would have now is like the validators have the state transition, and it could be completely valid. It could be an empty block if you want. And all of a sudden, none of the other collators or full nodes on that parachain have that block. And so if that were to get finalized, then you would have this parachain would be in a new state. It would have a new state root, but none of the full nodes or collators on that parachain would actually have the state transitions to create the state that creates that state root. And now you're basically like, you could never make another valid state transition again, because you could never create another POV that shows like the pruned state tree of how to get to your next one, because you don't have the previous one. So we need to make sure that like whatever data is finalized is available. And so that's why the title of the presentation was like cross shard data availability. So of course, like to get finalized, you're going to start asking for the shards that, or like the chunks that correspond to your chain. But you could also ask, nobody's going to stop you from asking for chunks that correspond to another chain. You can ask for, the chunks for any chain that you want to get a state proof for and validate. And so, of course, yeah, I think like the primary load would be people want to make sure that their chain is good. So if any collators aren't able to reconstruct this erasure coding, then they're going to start flagging it and tell the validators, hey, this was unavailable. And then that part's only focused on, is this available, but not on the actual validity of that block. That's where fishermen come in. So fishermen will also ask for the POV block. They'll execute it. And then if they think this is invalid, then they'll make a claim like on the relay chain and say, hey, this block is invalid. And then they'll put some stake of dots on it. So as you can kind of see, like collators are in a really good position to be fishermen because they're already asking for these chunks. Like they might as well, if they're going to reconstruct the block, they might as well actually execute it and make sure that it's valid. The only thing is that fishermen need to have some dots. Otherwise, they could just go around saying that like everything is invalid. They have to like put a stake on it that they would be slashed if the block actually is valid. Whereas collators, like they don't actually have to own any dots. They could be completely dot free if you like. But if they're happy to own some dots, then they could also be a fisherman as well. So yeah, so collators, and so now I have this thing called secondary checks. So collators and fishermen are going to send alerts that say like, hey, this is invalid or this is unavailable. But it's ultimately up to validators to like make sure that only valid data is getting into the chain. And so we start randomly selecting them again to actually check this stuff. So this is not like the 10 validators who were selected randomly on this parachain. This is after the candidate receipt is already in a block that's not yet finalized in the relay chain. And so we're just going to randomly select other validators from the set to say, hey, you need to reconstruct this block from this parachain and validate it. And so you'll just start to get other validators who start requesting the erasure codings and reconstructing them and validating them. And so this is kind of to get over the fear of like, you might have 10 validators on a single parachain. It's a pretty small number, like they could collude. The randomness helps, but also like lots of people in Polkadot run multiple validators. So it is possible that the same entity could actually have like 7 of the validators on a single parachain. And we definitely don't want them to collude or anything. So we're just going to like choose another random set of validators to perform secondary checks. And then only after enough secondary checks have been done can a validator even like cast a pre-vote or pre-commit for a block in Grandpa. So like Web3 did some analysis and just came out to like, this doesn't really depend on the size of the validator set. If you randomly select more than 13 other validators to do a check, then it would take over 50 years to get a successful attack. And then basically like if all say 14 of these validators say like, yes, this is valid, then it kind of like clears, and now you can do your pre-votes and pre-commits in a Grandpa round. But if any of them actually say that this block is invalid, then we kind of go into this like war, if you will, in the validator set where like everybody starts requesting this, and it goes up to 1/3 of the validator set. So as soon as more than 1/3 of the validator set says that a block is valid or invalid, then it's valid or invalid. If both groups, if you have more than 1/3 saying that it's valid and more than 1/3 saying it's invalid, then you've like violated your BFT assumptions that like less than 1/3 of the validator set is malicious. So as soon as more than 1/3 of the validator set says that the block is invalid or valid, then it's whatever that majority says. And then the other group is slashed like extremely heavily. It might even be 100% because this is like it's a deterministic yes, no, this is valid or invalid. And if you're giving the wrong answer here, then this is like quite clearly a large attack on the system. And so this kind of gives like you can visualize this as like the relay chain having 3 zones. So when a block is first created, it goes into this fishing zone where fishermen and collators are asking to reconstruct the blocks. And then the validators themselves will start asking to reconstruct the blocks. And then once enough of them have done secondary checks, it moves into this Grandpa voting zone where it's legal to actually cast your votes and like try to get to finality. And then, once it goes through the normal grandpa procedure, it can go into the finalized chain. And so like, I know it's a lot of like steps to talk about, but we actually like, if everything's going smoothly and nothing's invalid, then we expect this whole process from like block creation to being finalized to be about 1 minute. So pretty quick. The nice thing is that like it's dynamic. So if you look at like other systems like ETH2, they kind of finalize like a whole epoch in one batch, and they just say like this whole epoch is valid, and then they move on to the next one. Whereas here, like this block height can grow and shrink. So if all is going smoothly, it might just be like 3 or 4 blocks in each zone. Whereas if there are a lot of reports of invalidity, you could stretch this out where it could take like 5 minutes for a block to get finalized until we determine like what is actually valid. And so it just gives us like a lot of flexibility in how we finalize the chain. So yeah, then there's some extra. I'll go to questions if there are any. No. You should start asking questions because I think this next one is my last slide. And then we'll move into like more just like a question and answer session. Yeah, so all of this is like kind of driving around this one principle, which is that we don't want the relay chain to be a bottleneck. So you want to push as much information and data transmission to the edges of the network as possible. Like you don't want anything going through like a bottleneck. So like some of the stuff we talked about in here, like the relay chain information is always constant size. Like you're passing around these candidate receipts, and then like what's actually going to the relay chain is just a header update, which could just be like a single hash for each parachain. That collators and fishermen increase with the number of parachains. So, they're doing a lot of the work of reporting the invalidity. And so, as the number of parachains grows, like if we go from like 100 to 200 parachains, this actually doesn't put more work on the validators because you have the collators and fishermen who are like doing a lot of the availability and validity checks for their own parachain. And then the block production one at the top, I put these in a bad order. But we have the separate like babe and grandpa, where block production is not on the critical path for finality. So we can keep creating blocks. And before we finalize them, we can do all these other checks. So we don't have to like wait for that. Whereas other systems, I guess like most systems have, it's like block production and finality are part of the same thing. So like might make a block, and then before you can finalize it, you have to do all these validity checks. And so this is like a nice isolation that we have that gives us a lot of flexibility in other areas. Cross-chain message passing, like we kind of like hinted at a little bit. But if like you look at what's going into the relay chain, it's just like these, the message routes of like your outgoing messages. But the actual messages are passed directly. So if 2 parachains share any full nodes, they'll just pass this message directly through the full nodes. And then if they don't share any full nodes, then they'll go through, it'll be the validators who actually end up passing these messages. But the messages themselves are never going into the relay chain. And then you can imagine like a lot of chains would just share full nodes, like if they're heavily interacting. So like if you have like a decentralized exchange or like a stablecoin chain that, a ton of other parachains are going to use, they'll just spin up full nodes on those chains and they'll be able to pass messages directly between them. And then this last one I put on is kind of like for fun, like a Polkadot 2.0 thing. It's the Hermit Relay Chain, that something we're planning on. So like right now, we have like the parachain updates and everything, but we also have like a lot of like Polkadot kind of like first class transactions. So like staking, governance, sending dot transfers, whatnot. That's all going into the relay chain. And so we'd actually like to move all of that out into parachains. And so you would have like a balances parachain, a governance parachain, a staking parachain, and then like basically the only information that would ever go into the relay chain is just updating the parachain headers. And then so all of the Polkadot logic would be moved into parachains itself. And so that's pretty cool. It frees up a lot of block space in the relay chain, a lot of storage space to be able to add more parachains in the future. And then I think that was it for the presentation. So yeah, we can go into questions now. How do we register for Riot Web3 Tech for access to technical communication channels? I don't know. Dan or Hutch, can you answer that one? Cool. Are there more questions from people? Doesn't even have to stay on this topic. We can, if there's other Polkadot things you're interested in. A couple good examples of parachains. Well, there aren't any parachains right now. So there's not even a relay chain. So, but what are some good examples? Yeah, I mean, like there's the, there's like the Hermit relay chain ones right now. So like talking about getting like governance and everything into their own parachains. I think like the first wave of parachains that we'll see will actually be like more infrastructure based, so like stablecoin, decentralized exchange, smart contracting, both like EVM and WASM smart contracts, which kind of serve as infrastructure for like the next layer of applications. When you think about like composability, then you could have an application that uses a stablecoin that's like its own parachain, but it doesn't actually have to implement the stablecoin itself. When it's useful to be a parachain, yeah, I mean, so Polkadot really provides like the context for interoperability so that you can like interact with other chains in a trust-free manner. And I think like one of the main reasons is for the security and like that context of passing messages. Yeah, I mean, it's like one of the main reasons to be in Polkadot is to not have to deal with your security. All right, let's move to the next one. Does increasing the number of parachains slow down the network? How many parachains do you see as the max in theory? So no, increasing the number of parachains doesn't slow down the network. So max, I would say like probably like 100 parachain slots that can be executed in one round. But this is like kind of a pair of threads question where we could kind of see having like 30 parachain, like 70 like full-time parachains and then 30 parathread slots. But that could be, 10,000 parathreads and you're just executing 30 of them each block. And these would be blockchains that don't really need to have super frequent state updates. Although max in theory is loaded. It could be higher. And then like the other like scaling principle you could use is like to have nested relay chains. So a parachain that's actually a relay chain for a bunch of other parachains. And then like the interchain messaging from like a parachain that's in a nested relay chain up to like some other nested relay chain would be quite a lot higher than like directly like parachain to parachain. But you can probably be in like a cluster that is like your group of interaction. How do fishermen find out about inactive or offline validators? So yeah, right now we use this heartbeat system where validators are either online by like producing blocks or they just send like a heartbeat that says, "Hey, I'm here." We're gonna move into like more of like a challenge response type thing where you can just ping somebody and demand a response from them. Don't know exactly how that looks right now though. Salient differences between parachain and parathread. Yes. So parachain, it really comes down to scheduling. So a parachain can execute a block in every block of the relay chain. So we have this like set heads function that we talked about, and it's going around and like collecting candidate receipts for all the parachain slots. And a parachain basically just like it has one of these parachain slots that's dedicated to itself. So it's always going to get assigned validators no matter what. So it can execute a block every single block. So you have like the relay chain will have a 6-second block time. a parachain can also have a 6-second block time and just executing as frequently as it wants within that context. A parathread, parathreads share a single parachain slot. So you could have 100 parathreads in a single slot, and every single block they're going to have an auction to be able to execute their block. So a parachain has actually bonded a bunch of tokens, like they won some auction that gives them this parachain slot for 6 months. Whereas a parathread doesn't have to do that. It's more of like pay as you go. So a parachain is not going to be paying for every single block. It's just it has this slot and it can use it. Whereas a parathread, there's going to be an auction to say, maybe a bunch of different parathreads want to execute at the same time. So they're all going to bid different amounts of how many dots they're willing to pay to be able to execute a block in that slot. And then whoever the winners are the ones who will execute. So it's really like scheduling and the payment model are the differences. But as far as runtime goes, it's like the same execution. It's still like an execute block function. Parathreads are really good for a couple applications, like applications that want to onboard into being a parachain, but maybe they don't have enough funding to get a full dedicated parachain slot yet. Or the other way, maybe they are a parachain slot and they lost it to an auction. Instead of going just offline and leaving Polkadot, they can now be a parathread. And then the application that a parathread is really well suited for is just stuff that doesn't need super frequent updates. 6-second block time is really fast if you are a stock market oracle that's just going to report the closing price at 4 p.m. each day, or a domain name service where you just want to update the registry once every hour or something. There's no reason you need a 6-second block time to be to keep updating this registry. It's mostly read only, where people are looking up entries in this registry, and you can just make a batch of changes every hour. So yeah, hope that answers it. When someone wins a parachain auction, how long will that slot last for the auction winner? We used to have it you could bid consecutive slots up to 2 years in 6-month chunks, and then I'm actually not super up to date. You might actually have to update this every 6 months, but I don't remember off the top of my head. Either 6 months or up to 2 years. Sorry. Don't see any more. So I guess I'll give one more minute if there are any questions. Otherwise, okay. Are there any plans for auctioned parachain slots to run on-demand parathreads? Do you mean someone giving up their? That's interesting. Yeah, to have your own parachain slot and then let parathreads bid on using it. I don't know of any plans, but I like the idea. It's good. Oh yeah, yes, that's what you meant. Yeah, that's a cool idea. I would want to see that. All right, cool. Yeah, thank you everyone for attending. And I think my email address was on that last one, or I'll just put it up again. Joe@parity.io. Oh man, you've probably been looking at a infinite mirror the whole time. I forgot to stop sharing my screen. Yeah, thanks for coming.